anybody who is joining, I'm going to run through can.compute's code. I just docoded it and improved the inline documentation for it. And this is, I'm doing this over at Bitovi, so I can just kind of do an off-the-cuff run-through, and they can ask questions and give feedback so I know what to focus on for an explanation for how can.compute works. I'm going to start doing a lot more of these. My hope is to get through all of the really heavy hitters of can.js, compute, map and list, probably the define plugin, and then all of the live binding stuff, parser, scope, all of that, can live, all of that. So this is the first one. Let me share my screen and get into it. And again, anybody who's watching, just give me feedback at any time, and I'm going to be taking notes on the side. So can you all see my screen?
Yep.
Cool.
Yes, you can.
So, actually, I think I'll use the doco for it. But before I do that, I'll actually show the structure. So can.compute, the can.compute module and folder is kind of broken up into 4 different files, 3 of which we'll talk about. Well, three of which we'll go into. The 4th one is we'll save for a different time. There's the main compute file. This is actually not where almost any logic happens. As you can see, it's really short. All this does is provide the what we call the familiar can.compute API that you are all used to using, where it looks like a function. This provides that by creating a facade against the actual prototype-based can.compute. So probably a lot of you aren't even aware that this exists. This is something that Alexis did. There's a prototype-based can.compute that runs faster than the function computes, and even by making the function computes use the prototype compute instead of the old way it was implemented, there's still performance improvements. So that's compute.js.
Sorry, is there like a really fast way you can describe why it's so much faster?
Because you benefit from prototypes. You're having to create less functions and that kind of stuff when you're in your creation. So then there's the proto-compute, and this is where almost a lot of the logic happens for building the different types of computes. So there's all the different types of computes, like you can have a compute that just represents a single value. You can have a compute that actually is derived from a function's value and updates whenever that function updates. You can pass computes your own rules for how to bind and unbind and read and set the value the compute represents. So there's all these different types of computes. This get proto-compute does all of that, which I'll walk through. And then there is the get value and bind. This is where the core logic that is able to run a function, see all the observables that function is reading, and then bind to all of those observables to some callback function. That is this get value and bind function. And on a high level, this file also provides the you could call it it used to be called can reading. It's going to be called can observe. This is the signal to the compute system that you should listen to some object's event. You should bind on that. The compute should bind on that. So that provides this method and a few other methods to manage that list of bindings, which we call an observe info object. So that's the third file, and the one that we're not going to talk about, but I just do want to reference, is the read, compute read. This, given some arbitrary object and some properties to read from that object, reads those properties so that they're all observable, so that they're going to be calling can observe correctly. That's what read does, but that we will save for later. So with that, let's walk through some of the code. Where did it go? No? Sweet. I'm trying to make this as big as I can. Okay, so as I said, can.compute is just a facade. So I'm going to jump to can.proto.compute, which, well, I'll actually start here. So can.compute takes the exact same arguments that can.compute was passed to and passes them to the proto.compute. And then all it does is creates the actual compute function, and the compute function just calls the inner prototype computes set if you're setting or get if you're getting. And then we just make sure that the bind, unbind, and these methods are actually calling the internal computes methods. Right? This is just providing a simple facade. There's a few other helpers that are defined, kind of for legacy stuff, like if you want to make sure you want to take a compute that returns a value, but make another compute that only changes to true or false. This is a helper that does that, and everything else is mostly just legacy. We'll talk about asyncs. So this is all the can.compute file. Now, where things really get real is the proto.compute, aka can.compute. So can.compute's primary objective is, and this is like I always like to think about code as what is the purpose of some code. Can.compute's primary objective is to provide a way to make observable values, single point values. Right? You can make an observable value, an observable compute API that reflects an input element. Right? You can wire up compute so that if an input element changes, well, the compute changes. If you change the compute, it'll update the input element. It's a way to kind of, in one of our other trainings, it's like we call it the I rule. It's like it's a single place to, like it's a single representation, an interface for an observable value. And you could hook that interface up to other observable values that come from the DOM or come from other observable values or all these kind of places. That's its primary goal. Now, it comes with the ability to quickly set up a variety of different computes, and I kind of list all the different types of computes, but just to remind people, there's the normal computes that you're most used to. You pass it a function, and that compute you can either get or set. And essentially, if any of the observables change that the compute function reads, the compute will update its value automatically. Actually, I think if we scroll down, I'll actually kind of go through them when we get to the code. So there's these different types of computes. But on a high level, can.computes externally have a get, set, on, and off method, and bind and unbind are alias to on and off. And that's all that can.compute really should be, a get and set, on and off. Listen to it, change, or read or set the value. But then, internally, get configured a on, off, get, or set function. And by specifying, depending on what type of compute you're trying to build, you set up the internal on, off, get, or set functions to read whatever actual observable value you're trying to read, or start listening to the observable values you should reflect upon. So it's kind of like there's these internal methods that call these external methods that are designed to call these internal methods, and we set these internal methods differently depending on
what
we get.
Why are there both? Why do you have two of them?
Well, the public ones, the public ones do their own setup. So like think about on, right? Well, on, once something is bound, it should, for the first time, it should call this underscore on, and then it should set a flag so that it knows it never has to do that again. And it should keep the cached value when something's bound. Instead of actually calling underscore get, when get is called, it should use the cached value. Does that make sense?
Yeah.
So
So
that's
like,
why,
the private ones are pure. They're not. They're kind of stateless.
more or less. You can kind of think of them that way, yeah. So these things call these depending on some flags and states. So like, there's some other flags like that are useful, but really the main one is the value, and this is where the cached value lives, if there is a cached value. So let's talk about it. Let's kind of run through the code real quick and see how all this ties together. So the can.compute constructor function takes arguments, and all it's really doing is, depending on what the arguments look like, it's calling a different setup function to set up one of these different types of computes. So, for instance, if the first argument is a function, well, then it needs to set up a getter-setter function. And it just kind of forwards the arguments as they're passed up here. It really doesn't do much else. Actually, see, well, yeah. In retrospect, some of this code could even be cleaned up, and this function is a mess and it needs to get cleaned up. But it's way better than it was. So all it does is essentially branch, but inspect the arguments, and then branch to what type of compute. So just to refresh everybody's minds, so getter-setter functional computes are computes where you just pass it a function. Property computes, you pass in an object, a property name you want to read or set, and then the event name that you might have to bind to whenever that is read or set. Setter computes, you pass an initial value and a setter function that gets called whenever the value is set. And then there's the settings compute. Oh, I didn't actually document async compute. There are async computes, but those are an internal thing that only the define getter uses, is that form of compute, which we'll talk about. And then there's the settings compute, where you can actually specify those internal on, off, get, and set values and the initial value it takes. And then finally there's...
Sorry. Can you cover the property compute again? I'm sorry, that one's not familiar to me.
So, yes, let me kind of show an example. Is, you know, I don't know if you know this, but let's say I had an input element. Let's just say I got an input element from jQuery somehow. I don't know if you've seen this, but I could create a compute that is bound to that input element's value by, let's say that was the name input element. I could do something like, with the normal can.compute API, I would get the item, the property I want to listen to, and what actually event I have to listen to for changes in that. And now I could actually read, just by using this compute, I could actually read the, if I read this, it'll actually give me the input's value, and if I bind to it, I can listen to, it'll essentially be setting up and binding on inputs change internally. And if I update name, it'll update the input's value.
Cool, thanks.
Yeah. What is the call signature for calling this constructor with async computes? Yes, I don't want to spend time on the call signature, but I will spend time going through how async computes work. And then finally, there's simple value where you just pass in like a number and you want to be able to bind it. So anyways, all that these are doing is just kind of checking the arguments and calling the setup, the various setup methods, which these start off. So we'll start off with like we'll kind of start with the, well, I'm not sure how I should go through this, but you guys can let me know when I'm done. Part of me wants to like do a deep dive into how functional computes work, but part of me wants to stick on a high level with the compute kind of surface API and how that all works before I get into this. So I'm going to actually do what my instinct tells me and talk about not these setup functions yet, but how the what bind and unbind and those kind of things do, and how these internal methods are called. So bind setup, So a normal bind, if you use this can bind and setup, this is a special function that will call bind, the normal can event bind method, which underneath the hood, even I think, well, we used to call jQuery's bind method, but now we have our own because it's much faster. Anyways, this just calls a normal bind, except it will call an underscore bind setup method the first time this instance is bound to. So the first time someone binds, we're going to set a flag letting us know that we've been bound, and then we're going to call the internal on method. And this updater method is essentially a callback that is passed to the internal method that the internal method can call back anytime there's an update. It calls back this updater method. You might notice that it has this can not observe. This is a way to prevent if someone was like binding on or reading observable properties inside on here. You don't want them bound to. You don't, because bind should kind of not be, true, because then it would repeat the bind over and over and over again potentially. So that's why it's protected against bindings. Probably unbind should be doing the same thing, but it's not.
I'm not following. You're saying can bind and setup calls this underscore bind setup function?
Bind setup calls underscore bind setup, yes, the first time you bound.
So what is it for, though?
What is what for?
Can bind and setup? Like, why would you use it?
To create this functionality. So it's like, I want a bind function that's going to call bind setup the first time something's bound, and I want an unbind function the last time something is unbound, so there's no more bindings, to call this function.
But its purpose, it sets a flag, and then what's that flag used for?
What's what flag used for?
This dot bound.
Oh, well, we'll see that. That's really we can see that right away. So get, for instance, when we're trying to read a compute's value, if it's bound, it just returns the cached value. Otherwise, it goes and calls the internal get function.
Okay, so this prevents having to get the value every time.
Yes,
it sets up caching.
Having to call. Yeah, exactly. So we'll skip clone because that's not important. That's just for being able to create a new copy of a compute that has a different context. But that should hopefully go away someday. Anyways, get. Here, let's talk about how get works. So this is a helper just to let you know if any compute is currently trying to run its function and calculate if any observes are being found or read and trying to do the whole crazy computed logic. This lets you know if that's going on. If something is recording observes, and this is just a special flag because there's certain computes that you don't want observable by other computes. If you are recording observes and you can actually observe this compute, then we're going to do this little performance optimization. We're going to say that, hey, well, this compute is being read, so we're going to call can_observe, which says this, listen to this compute's change event. But we're going to do this little performance thing and say, hey, if you haven't bound to this compute, well, you're probably about to anyways because someone's recording observes, right? So temporarily bind this compute so that bound will be true and you'll get the cache value. Because you're going to be bound in an instant anyways by the recording compute, this, Dave, you might mute yourself so it doesn't thrash to you. Thanks. This is a little performance improvement because essentially we know we're about to be bound to, let's bind to ourselves right away.
But so the value has already been gotten at this point? We know that?
The value will be retrieved, yeah, because whenever you bind a compute, it by default gets the value.
Oh, okay.
Okay. So the default get just returns the cache value. That's the defaults here really don't mean too much. They're really the defaults for simple single value type computes. Okay, so now let's look at set. Set's a little bit more complex because depending on the type of the compute, what form the compute is taking, what flavor of compute, and what set returns, it might need to call underscore get, because right now we currently have a the set API is designed to return the current value. So if you try to set a compute, you actually get the current value back out of it. I think I'd like to change that for 3.0, so you don't you can set a compute, but you don't necessarily expect to get the value out. I think Chris understands a little bit why this is, but I'm not going to go into it here. There's just some performance optimizations you can do because we're not having to call the get potentially on every set. So what it's going to do is call the set code with the new value, whatever the setter was, the new value and old value. There's some special flag where, like, hey, some setters are actually going to set the cached value themselves. If it's one of those types of computes, well, just return the cached value because the setter is taking care of it. If this compute has dependencies, meaning really it's a functional form of the compute, well, you have to call the getter every time. This is what I'm talking about. I want to get rid of having to call these getters just to be able to always return the new latest value. But anyways, if set value is, if this didn't return anything, well, then you have to call the getter, and you're going to use that for your cached value. And then otherwise, if set did return a value, we're going to assume that that is the actual new cached value. And then we're going to, this update on change essentially fires the events on the compute. So you pass it the new value and the old value and your compute, and it'll trigger an event. And we just return the new value inside the compute. So this code I don't really like, but we can't really simplify it. I really think we should just make it so that computes don't return their latest value, and that will clean that up significantly. Okay, so that's the main stuff for the external things. Now it's really how do you set up on and off and underscore on and off and underscore get and set. And let's talk about the type of computes that everybody's most familiar with, the getter-setter computes. Really just think about it as the getter compute for the most part, where you pass it a function and a context of this for what you want the, you pass it a this for what you want the function's this to be when called. So this will set get to essentially call that function with the right context, and set to also do the same thing. Now where the real magic happens is the on and off, because when you're bound, when you first bind to the compute, you need to read that function and track all of the observables that are being read and update the value of the compute. So a lot of that starts with this setup compute handlers, and also happens in the get value and bind function. So let's walk. So the setup compute handlers returns essentially an on and off that does all of that. First time it's bound, get all of its observables, and start listening for changes and updating the compute's value when it changes. So let's take a look at setup compute handlers, which is a helper at the bottom. Setup compute handlers. So as you can see, it returns an on and off function. So when the compute is first bound, on is called, and it's going to call this get value and bind function, which we'll see in a second. And what that does is it runs the function with a current context and looks at all new observables that might be read and binds them to onChanged. You pass it, it also takes the old observables that it was binding to before, and if there were any differences, it takes care of binding on only the new ones, not touching any ones that are currently bound, and unbinding from anything that's no longer bound. That all happens in get value and bind, and we'll come back to that. So basically, get value and bind, when any of the observables change that this function might read, it calls this onChanged handler. And then it's just going to set the compute. This is what we passed in the compute itself. It's going to set the this returns the data about what was observed and also the value that the function returned. We're going to set that as the compute's cached value, and then we're going to signal if the compute actually has any dependent observables, or not source observables really. If as long as read-info observe has some observables in it, then we know this compute actually has, like, is binding, listening on something. So unbind is essentially going to go through that list of objects, observables, and unbind on, this is kind of like each item in here, each object, or each kind of observable map has an object property, that is what you bound to, and an event which you need to unbind to, and it's going to stop listening to changed. So let's talk about changed. On changed, this is the thing that gets called back whenever an observable changes. This is going to make sure that, I'll talk about this problem maybe, what info ready does here. This is an event ordering thing. This is actually, Chris, you were just asking me about something related to this. So let's ignore that, and I might come back to it. So this is going to make sure that the compute is bound and that the batch number has changed. And if the batch number has changed, it's going to repeat this get value and bind, but with the old info that the first one returned. So it's going to unbind anything that is no longer bound to, and then just keep like getting more things to call on change. Call compute's updater method, which is a way you pass it the new value, the old value. If there's a change, it'll trigger an event if these two things are different. And pass it the batch number, and then update the batch number. So get value and bind is where a lot of like the real, meat of this is, right? Again, this takes a function. What you should call the functions this with essentially the old things, the things you used to be observing on or were observing the last time this function was read, and what you should be binding, what you want to call back anytime any of those observables that you're reading have changed. So that all happens in get value and bind here. So get value and bind, because it's so performance sensitive, is really broken up into a lot of different functions so that they can be optimized. Because just so you guys know, anytime you have any for loop like this, Chrome does not optimize that. So it cannot optimize functions like this. So we do everything we can to do as little looping as we can. So this is broken up, this file, into get value and bind, the helpers that get value and bind calls, which are all kind of towards the top. And then it's broken up into the observe flags, or that can.js supports, that kind of help with detailing what is being observed or not. And there's things that can kind of like clear your observe object, or your observe info object. So let's talk about what an observe info, there's a stack of these things, but let's talk about what an entry looks like, because this is important for everything else. This is what a call to a function, what observables that have been read look like. It kind of keeps an entry that looks like this. It's an object with an observe property where it has the keys, which are the unique ID of every observable instance. So if it's a map or a compute, those have unique IDs on them. It's going to have that ID followed by the property, followed by the event that is being observed. That's in this is the key, but then the value is going to have an object property that is the actual observable that you want to listen to, and the event that we're listening to on that object. The reason why,
well, you're probably going to get to this, but what's the reason for having the keys like this?
The reason is so that we can quickly identify if we've been bound to this observable event pair or not already.
Okay.
And to make it even faster, I recently added a collection of all of the names and values we've started to add. we essentially there's also this names property that represents adding up all of these keys. This is also another further feature enhancement that lets us know if the data has changed. So
Is a compute that's dependent on observed?
what?
Is names a compute that's dependent on observed?
Names a compute?
It's a joke, maybe a bad one. Never mind.
Sorry, I'm not. Yeah, okay. I don't get it, but you can explain it to me later, and I'll have a good laugh. So let's get back to how get value and bind works. Again, takes a function, what you want this to be called with, gets past one of those observed info objects, which this will also have a value on it eventually, and the callback you want to get called back. So this is the corest of core of can.js, of pretty much all of can.js's functionality, because live binding uses can.compute, and everything pretty much uses can.compute. So what this does is it calls get value and observed with your function and your context, and this is going to return your new observe info object, which looks like this.
When you say your function, what do you mean by your function? That's not the compute instance?
No, this is the function the compute wants to see what observables it's reading.
It's the getter setter compute, or the getter setter function?
Yes, this is the getter setter function. All right, so just to keep things very tangible for everybody here, what I mean is when you do can.compute, and if you did something like turn, so you had some map, and you did something like this, this function here.
Yeah, but you don't have to pass a function. What if you don't pass a function?
Matthew?
Yeah, if you were talking, I missed it. Like you did the input example, that didn't have a function. What is the?
Right now we're only in the setup behavior of that one form of compute.
Okay.
So when we looked at proto-compute, compute handlers, and a few of the other forms of computes, like async computes, a few of the other computes use it, but some of them, like setup simple value, don't use that function. To create its on and off, because it doesn't need this, this type of observing function.
Okay.
So getting back to here, so get value and observed is called to get one of those observe info objects for the function, reading function and the context. So let's go into that and see what that does. Where did it go? Okay, get value and observed. Gets a function, it's going to run it. What that does is it's going to push onto the observed info stack the next observed info object, right? This is going to have names as an empty string and observed where we're not observing on anything yet, so it's going to be empty. Then it's going to call the function and then pop that back off. And then it's going to set the return value of that function as the observed info object, which we're calling stack item right here, its value, pointing to that value, and return that. So let's talk about why we're doing all of this, right? Why are we adding to the stack, and how is it going to suddenly look like this, right? Well, this is the key to everything. So when we push this on the stack here, and then this function, and then we're going to call that function. That function is going to run this code here, which is called map.adder and pass it first, and then call map.adder and pass it last. Internally, map.adder is calling can observe with the map and with the event that we want to listen to, which is first. So internally, inside here, can observe is being called. And can observe is going to check to make sure that there's something on the stack. It's going to take that map, and this is this would be first. This would be map, and this would be first. It's going to get this. It's going to create a name for that, which is the CID and the event. And it's going to get the last item in the stack. It's going to update its names to include the new thing, the new name that's being added, and then it's going to add that as a. It's going to take. This is kind of like a key. This represents kind of like a key value for a given object being a given object's event. It's going to add that object and event in that key on the observed object here. So those are all going to be stored. So it's going to add kind of two. It's going to add one for the first property and another for the second property on this observed info object, which is top right here. And then that's popped off. Where did that go? Then that's, yeah, go ahead.
Well, so it's going to have a key for everything that was read, right? The names is going to be populated with everything that you read inside your getter setter.
Yep, exactly.
Let's see what's happening.
So here's a question that maybe one of you, for some super brownie points, might be able to figure out. Why do we push? Why do we push and then pop? Why are we using a stack here?
So that it's the last item in the stack, because we want that object to have all the keys that are being read.
Yeah, but why not just use it in the?
All right. Yeah, I don't know.
Yeah, why not do it that way?
Because it's going to cascade like an effect of them, and you're going to build up that stack.
Actually, part of me wonders why. Actually, now I thought there was a good reason, but realizing maybe we don't have to do this anymore, or maybe at some point there was. Huh?
That was a much better joke than mine.
Oh, that was a joke? Sorry, I'm not thinking jokes
okay.
at all.
He's giving you a little smack there.
Okay. So the reason, well, the reason at least was at some point, now I have to kind of rethink this reason, is primarily because you can have a compute inside of compute. So you could have another compute, which is like, some compute, I'll call it info, that can be read, and you don't want it. Obviously, it needs its own kind of state and its own info object. So we maintain this stack. Oh, I know why we use a stack. Yeah, okay. The reason why we use a stack is because obviously read needs to be able to get what is the current thing. It needs to be able to get at that. At some point we didn't use a stack and just used like a pointer, and this would use a pointer, but I forgot why, but I used switching to a stack improved performance for some reason. I don't remember, but it used to move around pointers, but actually the stack was faster. I remember that now. So anyways, so we push it on to the observe stack so that essentially all calls to read will hit that. And then we pop it off so that any other calls to read are going to hit the next item in the stack. So that, if you have it goes into a compute, okay, well, now you should be binding to this compute and reading its value. And when I talked about that performance improvement before, we're like, oh, this compute is being read, bind to it right away. Well, it'll then call get info and observed on this compute's internal function, adding it to the stack, figuring out what it's bound to, setting up its cached value so that, essentially it doesn't have to be like we're not going to read through into the internal function of this compute to observe on that. We just want to bind on the compute itself changing, not in anything that this compute is reading internal to itself. So that's kind of why this is all set up like that. So anyways, this stack item is returned. This info object, right, with the value, but then also what's observed and all the names of what's been observed. And what it does is it checks if the new observed info object, if its names property is different from the old observed info object, then it's going to try to bind on what's new and unbind on what's old. So bind new set gets the old observed items and the new observed set and the unchanged event. So this needs to bind to anything that is in new observed set that is not in old observed set. So let's look at bind new set. That goes through everything in new observed set and calls this bind or prevent unbinding. And what that does, and this is given the key name, that kind of CID event name pair, it says, hey, if you're in the old observed set, we'll delete that from there and don't do anything. But if you're not in the old observed set, well, then we've got to bind on you to unchanged. So by deleting everything from that's already in the old observed set, that was in the old observed set that is in the new observed set, when we get to unbinding the old set, essentially we've already deleted everything that shouldn't be unbound to, so we just unbind to everything that's there. If that makes sense. Essentially, like, you think of it as like we're going through the new things and deleting them from the old things so that the old things only has left what's, you know, it actually is no longer bound to, so we unbind it. And we go through that and clean up all our bindings. Now there's this final thing where we do this ready event. This is the can batch after previous events. So you don't, it's possible, and this is kind of better explained in the 2.2 release article at the end of it than I'm going to do right now. It's possible that you are listening to, it's possible that you are listening, that you've just bound to something that is already got a queued event, is already being read, is already going to be fired off. But you don't want to listen to that, especially because you already have your value. So you shouldn't have to update yourself because you already have your value until all previous events have finished firing. Any events that have been currently tried to be dispatched should all fire before you try to update your value again. So this essentially listens till all previous events have finished fired, sets on your observed info object that you are finally ready to try again perhaps to find a new value, and returns this, that info object. And again, if we go back to get value and bind, if we go back to compute, photo compute, we'll see that that is get value and bind, returns that info object, but here it's also checking to make sure that, hey, we're actually ready. We actually have, since the time we set up our bindings, all previous events have finished firing. We can actually try again to read a new value. So that's how that works. Let's take a pause there, and maybe I'll finish up part 2 sometime later, because I've gone a lot more than 10 minutes. What do you guys think? Like, what parts, are confusing? Now's a really good time to, let me know what I should explain better in kind of the future video, that kind of thing. What didn't you understand?
Who are you going to be presenting this to?
I'm probably going to make a series of articles and videos that that will link from the can.js documentation.
What's this function that you're looking at right now?
This is that helper function, set up compute handlers that create
Set up compute
on and
handlers.
off.
Yeah. Okay.
So there's a lot of layers to this.
Yeah, because of that, one thing that might be really helpful for me would be if you had some kind of like an activity diagram that sort of described the flow. That might help me grasp all the various layers.
Okay. Cool.
What does updater do? Does that call when there's been a change?
Updater, yeah, it's essentially just a helper function that you can call on a compute with its new cached value and its old value, and it will trigger an event if it's changed. Any other?
So I know that like can.component is using this internally. My struggle with can.compute is finding where to use it outside like components and things that it's built into already. Like how else would it be useful?
That's not so much the goal for this presentation, like explaining how to use can.compute. What I'm really wanting to do is make it so that I don't have to, so other people are able to effectively program and improve can.js without me. And, there's different phases of where people are at, where some people, oh yeah, how do you use can.compute effectively? Actually, in a modern can.js application, you are not going to be using can.compute directly very much anymore, right? You're almost always using it through the defined get or, some other means, but it is the linchpin of what can.js is. All of live binding, a lot of the defined plugin, all heavily rely on can.compute. So it's like you just can't, if you don't understand how this works, you can't really improve a lot of the harder parts of can.js at all.
Did you explain read?
Explain what?
Read? I think you might have skipped over that one.
I talked about you're talking about, read? You mean this read?
Yes.
No,
So
I'm not
this
talking
is
about that at this time, no. That's for the future. So let me do a quick summary just for everybody here of what each layer is about. So that way, if you find problems, you have some idea where to look. So the compute here, now the can.compute.js is basically nothing, just a facade. So there's pretty much nothing there. The proto-compute is, I would say, broken up into, the constructor function finding its different arguments. There's the constructor function figuring out which setup method, the setup behavior to call. Then there's the different setup methods that do things differently, each one. Actually, we can take a quick look at setup property. So if that's an observe, it just makes its get read the property and set the property, and its on and off call that observable's listen to that observable and call handler, and handler just updates the compute. Each one of these has a slightly different functionality to set up, but then there's the essentially the get, set, on, and off functionality, which is pretty more or less straightforward, that call the internal methods. Get, set, on, and off, call these internal methods, and then finally there's the where I would say the magic of computes happens, which is in get value and bind for the most part, where it is doing that. Essentially, what you can think of it as diffing of, it's reading a function, getting all of its observables and diffing them to figure out what it should be bound to, like what new observables it needs to listen to, and what old observables it should be unbinding. And that's what happens in this get value and bind function. And then there's slightly these other things that are mostly the only two that you guys will ever really need a lot of are can observe if you're trying to create your own, if you wanted to create your own new type of observable, if you wanted to make it so the define plugin, for instance, worked on getter setters, object define property, if you want to make something that could do that, you would want to be calling this method. And the only other one you might see in our code is not observe, cannot observe, which basically you pass it a function and it returns to you another function that cannot be observed. Which you'll see that sprinkled in our code base for certain things that should not be observed. So that's a high level.
So what's the, like I was looking at some code where we set up creating computes for different types. Like you create a compute for a promise. Is that calling reading?
So yeah, okay. So read is where this is. So read is an interesting thing, which should probably be moved into its own like place. I don't really know where to put read, so that's why we put it with compute, because it is heavily related to computes. It's a way. So if you what you do with read is I can pass it any arbitrary. I can pass it any arbitrary object or map or whatever I want in here, and I pass it the properties that I want it to read, and I can pass it like certain other flags that say, hey, if it ends in a function, call the function. And this is essentially what the live binding system uses whenever you do foo.bar. It essentially is doing, it's passing your, it's passing an observable or something in here, whatever your context is, and trying to read foo bar, such that it's gonna, if this was a map, it's gonna read map.attrfoo.attrbar. And that's what read does, and you know, this is a talk for another day, not today.
Can you cover after previous events at a high level again? Because I think when you covered it, it was kind of like at a low level. And
you can think of it as, I'm not sure the best way. I can only do it on a low level, but I'll try to make it a more easily understood low level, I guess. Let's say I had a map, and I was going to, I was binding on it, on some foo. And then here I wanted to, I'm trying to think of the case. The problem, it's always like when you have sandwiched, okay. So you can see that, hopefully with this, that you could see that I would get the foo event before the bar event, potentially, right? So that both foo and bar is being dispatched, but foo is, how do I say this? But we'll get the foo event in here. Does that make sense?
Mm-hmm.
Now, think about a compute, or sometimes like live binding. You can think of it as actually listening on both foo and bar. And, well, yeah, in this case they are dispatched with the same batch number. I don't know. I would read that 2.2 article. I think it does I think it's going to do a much better job than I am capable of mentally prepared for right now to describe. I think it's like the last thing. I would read through that, and then if you have other questions, then I can boot up my brain. And yeah, here there's this whole section, batching improvements, where it talks about like the problems and how this addresses it.
Cool.
Yeah. So one other thing I'm looking for, which would be really nice if anybody wants to, I'm looking for people to work with me to kind of set up this inline documentation. Those would be really good open source contributions and a really good way of learning the code. If that's something somebody is interested, let me know. So cool. Anything else? Any ideas, other comments, things that weren't very clear? You guys feel like you learned something?
I feel like I have a lot to learn.
I feel like if I watch the video a couple times, I'll learn something.
I feel like I lost something.
You lost something? Well, the only things that I would say that are good takeaways, even if you don't understand can.compute, are some of the performance strategies that this uses to get good performance. Primarily, the one, it doesn't, it moves all four loops, four in loops out. That's why, like, I could move this code inside here, but I don't, because then this code could never be optimized. So that's why I move it into its own function and call the function. I don't do the same thing here because there's no code really to be, like, I could create a function, but the function would look practically the same, so there's no reason to do it there. And the other thing is just a fast way of doing a diff, right? So if you ever need to do a diff of two different sets, what you can do is run through the new items and delete them from the old ones. So I'm essentially running through the new ones and deleting from the old ones, and then you have in the old one everything that is like was not in the new set. This is how you can diff two sets in just two loops. You just have to loop through each item in each different set. So that's a pretty efficient way of diffing. Cool. All right. Well, and then again, if anybody wants to learn more about this, just ping me. I will happily talk your ear off. Thank you, everybody.
Thanks, Justin.
All right, bye.
Thanks.
Later.